Good evening once again. On behalf of the Spatial Analysis and Simulation Lab, SASL, I'd like to warmly welcome you to our live webinar titled Resilience of Building Energy Performance, How Can It Be Assessed for Improvement? The Spatial Analysis and Simulation Lab was founded by Professor 𝗕𝘂𝗶𝗹𝗆𝗆, Associate Professor at the American University in Cairo, and aims to be a leading center for interdisciplinary research focused on shaping healthier, more sustainable, and resilient cities, especially across Egypt, Africa, and the Arab world. Our work brings together digital tools, smart planning, and data analysis to better understand urban systems and develop useful solutions. One of the key goals we focus on at Spatial Analysis and Simulation Lab is improving environmental quality and reducing risks in city, especially in the context of the climate change. Today's webinar reflects this vision by exploring how buildings can stay energy efficient even during difficult conditions. It is a critical issue in today's climate. I am honored to introduce today's distinguished speaker, Professor Mohamed Hamdy, a full professor, academic leader, and a member of the Innovation Committee at the Norwegian University of Science and Technology, NTNU. He is also a shareholder and a board member at the software company LavaLoon. Professor Hamdy earned his PhD in combining simulation and optimization for dimensioning optimal building envelope and HVAC systems from Aalto University in Finland in 2012. He later worked as a senior researcher at Eindhoven University of Technology in the Netherlands, working closely with experts in building automation. Since joining NTNU in 2016, he became a full professor in 2022. Professor Hamdy has contributed to several expert groups under the International Energy Agency, IEA, including EBC, Annex 93, Annex 82, and Annex 80, and has published over 90 peer-reviewed articles with an H-index of 30 and more than 5,000 citations. Outside of university work, he helped set up MetaBuild GmbH in Germany to develop simulation tools and commercialize them. He also invested in the software company LavaLoon, where he helped launch a new department focused on smart energy and building solutions. His work connects science, software, and real industry needs. I have also had the opportunity to collaborate with Professor Hamdy on a peer-reviewed paper published in early 2024, and we are currently continuing our research with colleagues from Egyptian institutions. It is always inspiring to work with him, and I am very pleased to welcome him today as our speaker. With that, I am very happy to leave the floor to Professor Mohamed Hamdy. Professor Hamdy, the floor is yours now. You may start your presentation. Thank you.
Talk about performance, it can be defined by different key performance indicators. And when we focus on energy performance, it means all performance which is related to energy. And actually, why we use energy mainly is to achieve good performance or good comfort in the building and good well-being. So it's a very difficult to have a building without energy. So we need energy. Even when we talk about zero energy buildings, it should be called net zero energy buildings because no way to use zero energy. Then we will be in tent or something which is not comfortable and there is no good condition inside it. So we need energy. That's why we have net zero energy, not zero energy. Today, we're going to focus on resilience. So it's a concept which has different definitions if we talk with people from different disciplines. So we would like to focus on what do we mean by resilience when we're talking about building energy performance. Yes, here it's, if I continue this introduction, actually, this is about my publication and my experts in these different fields, mainly smart buildings, zero energy buildings, positive energy districts, circular community, and resource efficiency, and in my lately research, I focused mainly on energy flexibility, energy management, and energy resilience. And we usually use different simulation tools and different calculation tools. Some of them are commercial, and some others we customize them. So we work hardly on using what we have and also to integrate different simulation tool together. So here is about what's mentioned. Also, I try to be in contact all the time with industry, like our 𝗕𝗂𝗶𝗹𝗶𝗆 is a German company now. It started in 2015, actually. So, and I have been there after my PhD to help them to build and to create a team there. So, and they focus also on simulation and optimization, and then they put different features like energy flexibility, energy management. So this is very good also to be in contact and see what's needed in real life in industry. Now let's focus on what we mean by resilience. So if we go to the concept of resilience, it's somehow new thinking in our field. So first, we were talking about when we design a building, we don't want the building to fail at all. But when we talk about resilience, we talk about fail-safe. So, okay, we have to agree that there could be a failure. So if there is a power cut, or there is a big, the HVAC system get broken for any reason, or there is different ways, different reason for failure. So we will talk about them. But whatever the reason, we would like to talk about if we fail, we have to fail in safe way and be able to recover. And this is the main concept of resilience. So instead of we talking about fail-safe design, we talk about safe-to-fail design. And here, let's make this a chart, let's say, and we have this figure to show probability and impact. So if we have something, we are worried a lot about it. So the probability something happened is high, and then also the impact is high. So we are in this red part, which is high probability, high impact, and then we have to pay a lot of attention. And most of designers can look at this part. And when we talk about low probability, low impact, then we don't have to pay enough attention. But when we talk about resilience, which is low probability but high impact, because it's very risky. If some events happened, the performance of the building can degrade to very bad level, but the probability of that to be happened is not very high, but it's has a very high impact. So that's why we have to pay a lot of attention. And in recent years, with climate change and with different reasons also of energy, lack of energy and so on, so it become very risky, and even the probability is not high. It starts to be higher, but the impact is really high. And we will talk about different application, residential buildings or commercial, or also buildings in military in different remote areas. So I will come to this later. So let's talk about resilience design. So here we have different attributes. Actually, we need to talk about them. So these attributes, it's about efficiency and robustness, resourcefulness, and flexibility, adaptation. So many people make like a mix between when we talk about these definitions. So, but they are different. So when we talk about efficiency, we're talking about different, like we including preparation, absorption, adaptation, and recovery. And when we talk about robustness, is mainly about absorption. So here we will come to different things. On right-hand side, I tried to make a definition which fit for building performance in our field. What is the meaning of each one of these? So the main message, they are not similar, they are different. Even many of us, maybe they use the same, they use a term in different ways. So one of things in science in general, it's very, very important to have the same terminologies to define the same thing we talking about. So when we see to this figure, we will see resilience on the top of this pyramid. And on bottom, we have different attributes, and then different ability, and then status, and then resilience. So resilience is one of the definition, which including all this energy efficiency, robustness, resourcefulness, all these are included in the term of resilience. But how to be quantified? This is very risky. And at NTNU, we worked hard on this part. Of course, it's an building on what have been developed earlier in different disciplines. So when we talk about resilience, it's very important to talk about to ask ourselves 4 questions. So when we talk about resilience, we have to ask resilience of what, and resilience to what, and resilience based on what, and resilience in what state. So if we answer all these 4 questions, then we have the same definition for energy resilience of buildings. So let's go and see by this lecture what we mean. But before I go that, the major challenge to protect the building performance against upcoming changes is that there is different things like about preparation, how to prepare for such kind of changes, or we will call it events, and then resistance, and then absorption and response, and adaptation and recovery. So here you see all these terms are, for many of us, if we ask this question, and we do that in some workshops actually, and I'll give this, and then we some people get confused or define it in different ways. Okay, so let's start with the first question. When we say resilience designs, resilience of what? So when we talk about of what, we have to define what we are talking about. If we say building, what do we mean by the building? So it's only the building as represented as a one single zone, or it's different zones, or we talking about the building only as a building envelope, or we talk about the building including lighting system, heating system, ventilation system, or we also consider the power supply to the building, and this power supply is locally, or it's connected to the grid, and there is different control strategy to help energy management or not. So when we have to say what, we have to put this boundary, and all this need to be in our boundary, depend on the definition. Some people can just focus on building envelope, others can focus on the whole building performance and connection with the grid. So in this way, so even to answer resilience of what, even we're talking about buildings, but it can be defined in different ways. It can be on neighborhood scale also. Then the second question is resilience to what? And this is when we talk about resilience, we talk about disruption event happen. So when it happened, it's the system or the performance degrades. So there is degradation in the performance. So what kind of event we are talking about? Like when we ask it ourselves about resilience of what, so we define the boundary of our problem or our system, and then resilience to what, because there is a lot of disruption event. We can classify them into groups, natural and technological. If we talk about natural, it can be meteorological, like maybe wind storm, or can be a shower storm, and can be hydrological, and they're like flood and so on. And then it can be biological, like for example, when we had COVID-19, and this influenced the thermal indoor air quality a lot. Or it can be technological, like power cut, we hear about it a lot, or also specific failure in the system, which is mechanical system, HVAC system. There can be many reasons that happen. So before we talk about resilience, we have to define what's the boundary, resilience of what, and then resilience to what, because we cannot be resilient to everything. Actually, it's very tough. If we succeeded, then we will be really resilient. Okay, so it will be very good, but usually it's not easy. On right-hand side, actually, it was like a table generated by my PhD, 𝗕𝗂𝗶𝗶𝗆𝗆. She's graduated like 3 years ago now. And but still she working in Norway in SINTEF is a research center there. And she made this like literature review about different people working on resilience for buildings in different scope and different disruption events. So if we look at this right-hand side of the third column, let's say, we see some people work on resilience, but disruption event is weather, the second is earthquake, the third is climate change, and so on. So it can be different ones. If we talk about resilience to what we mainly focus on is about extreme events. It's extreme weather event. It can be like heat waves or cold waves. In Middle East, we focus mainly on heat waves, which is very, we have to be serious on it. But also in cold climate countries, because now in Norway and the Scandinavian countries and also North Europe, North America, resilience to cold events are very important, okay? Because it's a very serious, if the people are used to be in good comfort, even it's a very cold. So when storm came, it can lead to different things. The system of heating system is designed for a specific cooling or heating load. But if the weather is really cold, it will be more demand is needed. And also it can lead to different kind of like failure in the system. For example, when we have a lot of snow, maybe that we don't have accessibility to some resources, or we have a problem to deliver some kind of energies or some kind of technician to maintain a building and so on. So here we just try to put some events happened in USA and Texas, for example. That was one of very serious one and led to many people died. So this, now we have a question about resilience in what stage. So when we talk about resilience in one stage, so we have to know what are the stages to talk about resilience. In this figure, we can see that first of all, like when we have first stage, we call it initial stage. The second, we can call it during disruption event, and the third after disruption event, and then final stage, and we will talk about this. So as you see with this red disruption event start here, it's in this stage. So here is the definition of initial and phase 1, phase 2, and final stage. But also, when we talk about this, let's assume the performance. We have to give example, then make it easy, right? So in this figure, you see in front of you, we can say Pn is the performance. This is the level or state which is comfort and achieve well-being, okay? So if we talk about temperature for thermal comfort, it will be the set point temperature like 22 or 21, okay? And then performance level on this y-axis, and on x-axis the time. So we assume we will be okay in this initial stage, and then when there is disruption, there is degradation in performance. So that's why temperature drop. So the building become very cold. To the limit, which is T2, we define it in this, and then when we have to event is finished, then the building can recover, but can recover fast or slow. This we will talk about. And final stage, after everything is finished and we came back to the initial stage, what we going to do and what we learned from this. So based on resilience definition, the building is able to, if we say the building is resilient, we can say building is able to prepare in the initial stage. So it's well prepared. And then it can absorb and adapt during the disruption event and can recover after the disruption event. So here we go to the next one, is when we say design is resilience based on what? So this is the fourth question. When we say about that, as we see in the previous slide, we have a performance indicator. So what is the performance indicator? Is only temperature, or temperature and also indoor air quality like C2 level in indoor? Can be different key performance indicators. They are so many, can be used. So based on what, it means mainly here, what is the key performance indicator we are talking about to define our resilience. And this resilience assessment can be quantitative or can be qualitative or quantitative. Here we focus as usually we do in our group, we focus on quantitative approaches. And we like to collaborate with other people and many to talk also about qualitative, because it's very, very important. Sometimes qualitative is more important because it's either yes or no. And quantitative, it depends on how much. So here also in this table 2.3, you can find a lot of people working on different key performance indicators. So if we think about indicator to define resilience, we have to think what is what should be in this indicator. So we have to, when we define what is the resilience metric in order to assess the resilience in all these 4 stages, we was thinking about what kind of indicator or metric we have to define. So we put some criteria to be exist when we have developed this one in our research group. So first of all, we said, okay, we need this metric to help decision makers in benchmarking resilience, because when you say resilience is good or bad, but what is the benchmark? Is relatively good compared to what, or if it's bad compared to what? So it's very important when we make quantitative assessment to talk about what is the benchmark. Considering all the stages, it was a challenge. That's why we had a project that was actually finished 3 years, and we had a PhD. So we started this work actually about, let's say, 7 years ago, okay? And this benchmark of resilience, we said, okay, it should help decision makers in benchmarking of resilience level. Resilience metric should not only capture the performance during the disruption event, but also after the disruption event, because actually resilience is like human. Sometimes you say about a person, he is resilient. So, and when you say this person is resilient, you have to look at how you define his success. He's successful in terms of what? Then there is key performance indicator for this. If we talk about students, so we can talk about their grades. Students, they study and maybe they have a lot of personal problem or many things could happen. So this is disruption event. But some of them can be resilient. It means, okay, they fail a little bit, but they can recover quickly and they can cope, and then they become smarter to learn how to deal with such kind of hard situation. So even resilience, we have it in our personal life. So the same when we're talking about resilience of building performance. So, and also here we're talking about the building scale should, this resilience should deal with different building scale. So we had this in our mind when we defined when we tried to define our metric for quantifying or assess the resilience. So how to be quantified? That was now the question. So we had, as I said, like many years ago, 7 years ago, had a PhD as Shabnam, and actually she finished in 2022, so it's 3 years. And this thesis has a lot of things about literature review, about resilience of building, and also about definition. So here you see here main goal, it was about to work toward resilient building performance and to make definitions, framework to assess, and also metric to assess resilience. So many of the coming slides came from this PhD thesis when we worked on, and now we continue the work on this. So the building is defined to be resilient if it's able to prepare, absorb, adapt, and also recover from disruption events. So this is the figure I presented now, but here with some more details. So TSP, so we're talking about temperature as a key performance indicator. And then TRT, which is habitable. So in this level, it's acceptable level, and this is habitable level, and this is unhabitable level. So it's very difficult for people to live in this condition. It means the temperature is very cold. If you're talking about heat cooling system, it will be the opposite. Then the temperature is very high. So this is an example of how disruption could happen. Actually, I like this webinar, and we are not so many, let's say. So it's very easy to stop me, and then we can discuss any points if you wish. So I don't have a problem to do that. When we worked on this framework, this was one of the first papers published in Building and Environment. It's about thermal building performance, how to be quantified. So here is again about what is TSP and what's TRT and THT and minimum. And let's talk about this with example. So this is again, like I presented this figure because it's this is the figure we used to create our framework. But when we focus on these stages only, we found it's not accurate enough to make assessment. So we had some segments. So let's start with, this is an example when temperature is set point 21 and then disruption happens, then we go down. So when we go down, in the first area, we see S1, which is the first segment in this, and then S2 and S3 and S4. Why we did these segments? Because if you stay, when we talk about, it's not about just how much you make degradation in the performance. So we have to know how long you stayed at each stage. So in S1, this is the time, so we spend this time, and then S2, we spend less time, but it's more difficult time, let's say, right? And if we go to below TR, this habitable level, if we go to this second stage, again, we have S3 and S4. That means depend on how long we stayed in each part. And when we go to to recover, so after the disruption event is finished and I reached the minimum temperature based on the system, I recover, then we have also S7, S8, and so on. So the question now, what is the hardest period do you think I can stay in? So I'm not sure if there is interaction possibility to talk with other, but maybe I ask question and answer it to make it easy. Here, if we talk about S6, for example, is one of the hardest times because I actually is unhabitable level. So it's a very hard to be there. So if you stayed long time in this condition, it will be too bad. So some people can say, okay, S7 can be like S6. Yes, but reality psychologically is not the same, because in S7, yes, you are in the same range of temperature, but actually you feel that the disruption is ended and you recover. So you feel better. So you can stay in S7 longer time, or you accept it more than S6, for example. So here we considered also this psychological part, and that's why from S1 to S6, we have penalty of 0.6, but in the other part, when we recover, it's 0.4. So it's less harmful, let's say. And then about the hazard penalty, it's like when we talk about S1, S2, so we define the factor for each one. And when we talk about exposure time, how long you stayed, and each one, there is also different penalties. And based on these weights, we define our concept. So in this figure, you can see here it's called like weighted unmet temperature. So based on these weighting factors and summation of how long you stayed in each phase, then you can assess how much your building is resilient in terms of temperature. So, and also the disruption event only broken in heating system, power cut in the heating system, so that was only one event, but the same for other events, we can apply the same approach. The other challenge is that if we focus on temperature, it's temperature of which zone. And if we have a big building, we have different zones. And people stay in each zone in different times, right? So in order to consider different zones with different temperature set point, because it can be range is different. So all this can be considered. And also the temperature is not fixed. Like when we say TSP, for example, it's not fixed, it's adaptable. Adaptable based on this figure chart in right-hand side. And this is called like adaptive thermal comfort level. to consider a change of the weather because people accept different temperature and different level. Any question about this? Yes.
Professor Hamdy, I guess we have a question in the chat box from Dua.
Yes. Yes, please.
She says how we physiologically feel that we can be recovered as we be in the same condition of heat exposure.
Yes, it's about you know that the disruption is ended. So, for example, you got information that the power or disruption is ended, and now you start to recover. So you feel that was another collaboration with people working, not engineers, but it's about psychologically you feel okay. You are you have hope that at least that the condition is improving. So you are in improving phase. You accept. But such kind of weighting factor we put, it needs more research actually, and that's why we started a new Annexes international work group with a lot of people on this part. So here in this PhD and this work, we define different weights, but these weights need to be tuned further. Okay, so maybe we define it 0.6, 0.4, but it can be less or it can be closer. Okay. I hope I answered quickly, because here we focus mainly on to consider everything, but how to be tuned and how to be accurate for each perspective. This can be defined, can be tuned later. Is there any other question?
No. You can continue.
Okay.
Thank you. Thank you.
You're welcome. So here, for example, also when we're talking about this temperature, maybe some people think that this temperature is fixed, like 22 all the time. But actually, it's not true, because even it looks like a line, whatever TSP or RT, whatever, it's adaptive one. So you can consider this line is threshold with it's changed this threshold during the time based on what is the outdoor temperature. So for people familiar with what's called adaptive thermal comfort level, they know that people accept temperature within a range, and this range is different depend on what's the running mean outdoor temperature. So it's the temperature of outdoor considering what happened in previous days, and we give a weight for each day today and also the previous days, because it influences also the behavior of people. And that this is another kind of research. Is already a lot of people work on this part, but we used the knowledge is generated there. But it's very well known when we talk about fixed temperature level and adaptive thermal comfort level. And then in order to have these different segments, we considered also for different zones, and we differentiate between this zone is occupied or not occupied in order to consider the percentage of different areas. For example, if we're talking about residential building, we have to know that the thermal comfort in living room is different than in the bedroom. So when you are sleeping, you prefer a lower temperature, actually, then it's more healthy for your deep sleep. And also, for example, in kitchen or toilet and so on, so it's different than each other. So all this is considered in this indicator we are using. In the end, we here we assessed the resilience based on this weighted unmet temperature. And here we succeeded to make some kind of benchmark system, because the framework, if I go back here, the framework actually is fixed. So we make some kind like test. If we buy any product, we will see it's efficient, high energy efficient or not, because it's tested in laboratory. Here also we have, based on simulation, we have simulation-based test. So we define what is the framework, how long we have before disruption event happened, and then when it's a disruption, it will start for how long time, and then when it recover, it depends on the system. So it's not controlled, and then in the final stage, the system are able to get smarter and deal with the next round or not. So that means we put the same condition for different building to test all of them for the same disruption event. In the end, we have worked on this, and we make it relative indicator in order to make benchmarking, and then we suggested some kind of grade or label, like usually we have for energy A++, A+, and B and C and so on. So we did the same for resilience. How much? Because we at that time we worked also in IEA, International Energy Agency. There is different like research groups working on this. This is international organization with international expert groups. And one of aim is how to make a label system, not for energy efficiency, but for resilience. And we participated in this, and that was part of our participation. Okay, so now we're talking about this framework, how to be applied. We're talking about 4 days power failure, because we selected this to be our disruption event, can be different. During the 4 days, the highest heating demand is started in this time. So we make the same. Here you can see the definition of this test framework. 1 day in initial stage, 4 days power failure, and then 4 days in phase 2, and then 1 day in final stage. And we put all these conditions, and this table showing the thresholds for different zones. Because when you want to test, like exam, when you give exam, you give the same exam for all students. So also when you test the building, you have to put the same conditions, the same time frame, the same hardness of question for all, in order to make benchmarking and compare between them. So this is the same what we did. In this figure, it's the results of one of our use cases, case study. So temperature, as you see, started on 20. We're talking now on the figure, right-hand side on top. We see the temperature is about 22 in first phase, and then there is failure happens. So temperature go down. So there is degradation in performance. If we look at the line, which is black, and then there is another one in blue. So the blue one, it shows what if the building has a battery, for example. So it can stay a little bit more with good temperature, and then when degradation started, it will be like going after. So there is delay. And also when we recover, we have a faster recovery. The second figure, actually, if I remember well, I think it was focusing also on what if the building has a photovoltaics, and compared with building without photovoltaics. And then we compared what if here is photovoltaics and this one with battery, and then what if we have both. So we did this test with different also like adaptation measures, like MBV, model predictive control, how it can improve the resilience, and this some kind of smartness. And then it's also, we have now also tested for phase change material and many different technologies, which can improve resilience of buildings. And here in this figure, you can see if you have passive house with PV, passive house with battery, passive house, standard PV, and I go from top to down, okay? And then a standard battery, and then a standard house. So we go from C, which is 1, and C 1.2, and then we go to level is A+, which is 8.7. This is our indicator. So it means if you have a battery and also you have your building is passive, it's very energy efficient. This building can be more resilient than the same building with less technologies. Is there more question in this part?
Yes.
Yeah,
We have
okay.
2 more questions. We have a question from Amani Khalil. Which city was the case study in, please?
This one, it was Oslo in Norway.
Norway, okay. And we have another question from Dua, how we can calculate the occupant hours at a larger scale, like urban scale?
Actually, we didn't work on urban scale until now. So it was this study, it was a building scale.
Okay, thank
so
you.
For urban scale, maybe we can build collaboration. Actually, I mentioned about IEA Annex we worked on. It was about resilience cooling of buildings. now we have a new one. It's actually two new ones. One is called the resilient cooling for cities. So here we talk about urban scale and also larger scale, city scale. And we have another annex, which is I involved heavily in this one, is called about resilience or in cold climate countries and remote areas. And this mainly about remote areas in cold climate countries, because it's become very critical actually nowadays. Because when ice will melt, actually, more people will live in these areas. So we prepare for such kind of situation when these places has less ice and it's melted, let's say, there is a lot of resources come below this ice, and then there is more people will go to live in this to get this resource. So there is a huge work on this area also.
Thank you so much, Professor Hamdy. We have a request from Mariam Ahmed Sameh. Can you share this publication with us?
Yeah, sure. Yes, the paper is published and the thesis also is published. So both are online. I can share both of them. Yes.
Okay, thank you so much, Professor Hamdy.
Yeah, you're welcome. And just because here, actually, I assume most of us from, I'm Egyptian from Middle East, and I think many attendants also from Middle East. So we applied the same. It was a collaboration with USA. With University of New York College of Environmental Science, and this study here we focused on the same concept what we applied for cooling system. So here the main paper were published. It's impact of building retrofitting on thermal resilience against power failure, but here we're focusing on air conditioning system. So it's what I presented before. It was about heating system. Here it was mainly about cooling system. The same approach is applied, but and the same indicators. So it's the same methodology, all the same. But here, as you see, when failure happens, temperature go up instead of going down. But now also we try to make it more multi-dimensional, so we can focusing on temperature, humidity, and indoor air quality. So this will be in coming publications. Okay, so just all this, it will be is the same case about air conditioning system. So as you see here, temperature go up. And here also we focused on different building envelope and also different technologies. Here we focused on phase change material and electrochromic glazing because both are very helpful to make building more resilient if we're focusing on overheating, not to temperature go down. Okay, so more or less this is the same, and here also we succeeded to make benchmarking for building. It's air conditioned building. This is existing condition, and this is if we made some renovation. And here if we implemented phase change material and we mix it between phase change and passive house. So as you see, we can go from resilience, which is poor resilience, and then by different technologies, the resilience level can be improved. And here, as you see, there is numbers. It means it's quantified. So we can make a benchmarking between building and see what is the real impact of each measure we implement. Okay, so this is all about resilience. So if there is any question, I will be happy to answer.
Thank you so much, Professor Hamdy.
If you want just like to make general also about our work in general at NTNU. Here actually we focusing on the Euro Council goal, which is to make climate neutral cities and also to be resilient by 2025. I'm lucky to be working in NTNU, Norwegian University of Science and Technology. It's located in Trondheim in Norway. And Trondheim is selected as one of cities to be a demo for neutral climate cities. So EU asked Europe to create 100 demo. It means 100 city to be a demo for other cities and to be climate neutral. And one of those is Trondheim, where NTNU is located. And there is different for EU goals. There is one goal, it's called 100 climate neutral and smart cities by 2030. So this is a big framework or like big goal we're focusing on. So when we talk about built environment, we as one of the first goals to be climate resilient, and then to be flexible. Then there is energy exchange between building and different application. So we focus on this part of resilience. Here also about international collaboration, focusing on the concept of resilience. There is two, which we as the NTNU part of those. It's Annex 82. It's called Energy Resilience Building toward, Energy Flexible Buildings toward Resilient Low Carbon Energy. This one is close to be finished now, 82, and now we have 86. And on right-hand side, you have Annex Resilient Cooling of Building. It's 80, and now we have a new one on city scale, as I mentioned. Here, I would like to appreciate also like our national project at NTNU is called Zero Energy Building and Zero Emission Neighborhood. So as you see here, we go from this scale of building to neighborhood scale because there is more things to be done. Okay, so now thanks you for your attention, but I'm very open for questions from your side.
Thank you so much, Professor Hamdy, for that outstanding and insightful presentation. It gave us a clear and practical understanding of the challenges and solutions related to energy resilience in buildings, especially under changing conditions. It was both informative and inspiring. Now we will begin the Q&A session. You are welcome to either raise your hand and ask directly or write your question in the chat, and I will read it aloud. I will make sure to go through as many questions as possible. I guess we have a question here from Dua. She asks how we can identify the long time of exposure that can be safe, like the 4 days of SET identified in passive survivability, how we can identify such threshold to be locally adapted.
Yeah, actually, this is very critical question, to be honest. And here in this work, as I mentioned, we built the framework. But as I said, different thresholds and indicator need to be customized locally. So this is like localization of indicator for different region. And to do that, we don't, as engineers, we don't have to work alone. So we have to collaborate with people has different background, even from medical school, and also like from psychological point of view. And that's what we try to do in these annexes I mentioned, like IEA Annex. We work in a group from different disciplines to localize these thresholds and the time frame. So I cannot give you direct answer. I have a publication on that. So at that, if we go to our publication, you can see our references where we got this threshold for now. But as you mentioned, if we go to another country, we need to adjust these thresholds. But it will not be just engineering work. Yeah, that's what I would like to say.
Sure, thank you. We have a question from Professor Nabil. Professor Nabil, the founder of the Spatial Analysis and Simulation Lab. Professor Nabil, you may unmute yourself. Yeah.
Yes, thank you very much, dear Dr. Randa, for moderating this session. And thank you, Dr. Mohamed, for being with us. It's really an honor. I have a general question, actually, regarding junior researcher. If an architect just graduated and would like to enter this world of thermal comfort, sustainability, simulation, what sort of skills they need to gain? Because as you know, that undergraduate studies might not provide them with the necessary skills. So what do you think that they should learn more? Just like programming or going to more statistical issues, or how they could start building their research career within this road of sustainability?
Yeah, thank you very much for this very critical question as a professor here. It's actually, we had a lot of discussion in this, and at NTNU, at least, we collaborated from different disciplines. So we are sure that people has to know about many things. So that's why we have collaboration with different departments. But to go directly and answer the question, actually, first of all, when we're talking about building, it's not about just building envelope, like what's the properties of wall and thermal mass of the building, and also architecture, how you design the floor plan if you are architect. You have to know about how an energy system works, and how your design and your material affect this the overall performance. And what kind of key performance indicators? Like many people from different fields, they are not familiar with key performance indicators need to be used, and the new one, like adaptive ones, for example. So the solution for that actually is to, why I think we all have like these credit hours, and to have programs which is focusing on built environment in general. So you take some courses related to thermal comfort, for example, and other courses. So if you talk about built environment, you have to go through this. And then there is some courses which is mainly simulation based, like simulation, building performance simulation, which is also like project based, where a student from different discipline, after they gather different information, they working together on a project. And a simulation, I believe it's a very, very powerful tool, because you can try, it depends on how this semester project is designed and given to the students step by step, to let them work together from different disciplines. In our building performance simulation course at NTNU, for example, usually we have people from different disciplines. We have some courses we are sure they got or they have it before, but also when we make a group work, we put people from different disciplines to work together and to learn from each other. And the task itself, it shows how to make a building, and then how to achieve comfort, and then how to be more energy efficient. And then when we go to zero energy and different renewables, how to be improved using different simulation tools. So mainly a quick question, like quick answer, is about thinking about this multidisciplinary and having these courses, which is have different backgrounds, and let people work on a project using simulation tool to try and error. But this try and error, to be honest, need to be very well structured in order to teach the student what they have to learn step by step. Because if you give just like big challenge, we need this building to be energy efficient and so on, they can go and not in systematic way. And then it's difficult to learn, but it depends on how you structure the assignment for them. It's very critical, and how to group them and let them to work together.
Yeah, thank you very much.
I hope this is helpful, yes.
Yeah, no, this is really interesting, because I mean, our students are really capable, but they need some sort of a guidance of how to just take the first step in order to achieve the goal at the end, being a researcher, good researcher. Thank you very much.
Yeah, thank you. It's like a puzzle, and how to connect it by some exercises. Yes.
Yes,
Thank you so
agree.
much.
Thank you.
Thank you, Professor Nabil, for your question. Thank you, Professor Hamdy, for your informative answer. We have another question from one of our participants. Given that thermal comfort is inherently adaptive and influenced by behavior, physiological and contextual factor, how does the WUMTB model avoid penalizing short-term deviations that may be acceptable or even preferred by occupants in real-world adaptive environments?
Yeah, but to answer this question is what we using is we use adaptive thermal comfort models, actually. So if we talk about fixed temperature level, it's just we're talking about temperature like 21 for heating system and 24 for cooling system, and they fix it all the time. We don't use those thresholds, but the threshold actually is function of running outdoor temperature, which is representing temperature during the previous 7 days. And also about it's considered by thermal comfort model, it's already considered also a different adaptation method, like if you change your clothes, what you have. So all this can be defined in, you can choose what is the adaptive thermal comfort model you want to implement with the framework of assessment, resilience assessment. So here we used adaptive, And this adaptive is different from zone to zone or from application to application.
Thank you, Professor Hamdy. We have
Yeah.
another question from 𝗕𝗂𝗶𝗶𝗆. Given the recent redundant power failure in Cairo, Egypt, and the concerns associated with it, what type of research you think is necessary to tackle this problem, or how can researchers inform policymakers and architects and engineers in practice?
Okay, so and now we focus on Egypt, right? So I think in general, like there is two things actually. One is on education level. So in my opinion, we need to have this comprehensive thinking and to teach this to our students, how to quantify and how energy efficiency and energy resilience is very critical because of different power cut. And then we need to localize these thresholds and for different like location, let's say, or for Egypt, let's say, if we talk about Egypt. So first of all, we need new generation that they have this knowledge and they are able to implement it. So because this is the first step to have this knowledge between our student and the graduates. On like higher level, like when we talk about legislation and so on, there is different like when we talking about upgrading building, but actually it's not very active, but we have a potential actually when in the real estate market in Egypt is growing very, very fast actually. And when we talk to decision makers and the legislators, they have to get informed during this phase. When you build more, you are in the best phase to prepare to make your building energy efficient and also energy resilient. So how to make conferences from like professors in universities and so on, and spread this knowledge to decision makers is very critical, because people in consultation and so on, they will not go to do it except if it's required, and it will not be required if it's not in the legislation. But actually, in some good news, let's say, in Egypt nowadays, like there's approach for making more hotel apartments, like to allow people in Egypt to pay subscription and make test for the building. And if it's a has high quality in terms of many things, and one of them it's energy efficiency, it's coming. In this case, this building will be upgraded in terms of energy efficiency. And once we have this, it will the knowledge, people will do that from business point of view, because they want to rent their apartments for foreigners, let's say. And when we implement this in public building, we will have a lot of demos. Then people will see how much this is important. Another thing is about energy price. When it's come higher, of course, by nature, people will see, seek for a solution which is good in this term of energy efficiency and energy resilience. It's a difficult anyway, but anyway, it's based on to have a good graduated, which is knowledgeable, and also to spread this knowledge for the decision makers, and then to use opportunities in industry based on the current new regulation. So if we work on these three, I think we have to work on three in parallel to speed up this change. Yes.
Thank you so much, Professor Hamdy. We have another question from 𝗂𝘂𝗶𝗆. As identified in Annex 80 workflow, you mentioned generated weather data that account heat waves is very complex process using weather data like this cortex can be used morphed techniques and can be same reliable for climate resilience and accepted to publishing research. Can you please guide us to whether future data model that can, in case like Egypt or Cortex, data is difficult to reach?
Okay, so actually there is some model. So in Annex 80, for example, we had subgroups, like 4 subgroups, and one group, it was focusing on how to generate weather in future. And there is like weather generator, like it's a simulation tool, can be used to generate weather for future. But the challenge is how to localize it, for example, and also how to make it on our scale, not like daily scale. But there is a lot of work has been done in this. So maybe if someone would like to contact me after, and then I contact them to people working on this area, I will, it's my pleasure to help in this regard. But I know there is some challenges like for localizing this local weather, but some people work on that, yes, for sure. And to answer, is it okay for research or not? Yes, because when you make resilience, you make scenarios for future. So it's on not only one scenario. So we have some uncertainty in this. So as much as you do your scenarios in good way, it will be acceptable, because anyway, it will be a prediction.
Thank you so much, Professor Hamdy. I think we have a question from Mariam Magid. Mariam is an RA at our lab. Mariam, you can unmute yourself here.
Thank you, Professor, for the amazing talk. I have a question. As a future vision or in a large-scale facility management, what strategies or innovations have proven, or do you envision most effective in ensuring long-term resilience in energy performance while minimizing operational costs? So any emerging innovations or technologies that will augment this approach of assessing resilience?
Actually, it's thank you for this. I think for now we try to collaborate with facility managers to spread this knowledge between them, because it's not very they don't know a lot about how to make building or energy resilient. So they focus more on another kind of resilience, like against like earthquake or some big problems like this. But in terms of energy and climate change, still we need to work further. But by using this simulation tool, what we try now, we try to connect it with building automation system. And because most of big projects, they have already a building automation system. And there is a lot of measurements for prediction. And also, if it's connected with like concept of digital twin, it will make a prediction for future to say, if this happened, the building will be resilient for how long. And then facility managers can define what kind of resources or what kind of adaptation measure need to be implemented in order to face these problems. But of course, they start with the building, which is more critical and more important. Okay, so depend on the value of this asset, then people pay attention to this. So they pay attention to other things before energy resilience, actually. But one of our things or effort we do is to connect with facility managers and to connect our work and our key performance indicator as a plug-in in their tools. And one of them is building automation system, and also feature digital twins. So it's still an ongoing effort on this regard. Yes.
Thank you so much.
Yes.
Thank you, Mariam, for the question. Do we have any other questions? If no one else has a question right now, I'll go ahead and ask one to wrap up. Professor Hamdy, in your experience, are there lessons we can learn from European practices that could apply to hot arid regions like ours?
Yes, actually, it's okay. So if I ask about the knowledge itself, is about key performance indicator to be adapted for our clients, for our clients, then it's the same approach like what I showed here. For example, what we made for cold climates, it can be applied for hot climates. So and then it need to be localized by also the first question about the weather generator, and to be localized and how to implement this for example, if we talk about Egypt, and we have to see what kind of coming regulation, like the one which I mentioned about building renovation for renting houses for tourists and so on in future. So when we connect this knowledge with this, what's coming in future, this could make changes. But for us, I think the most important is to focus on like knowledge transfer from Europe to take, for example, the same approach can be applied for hot climates. And then there is different challenges you will see to localize this approach for hot climates. And I think we work on this also, like as Dr. Rolanda, one of coming paper, it will be on this regard.
Yes.
Yeah.
Thank you
But
so
yeah,
much.
definitely, yes, what is generated outside, it can be applied for our, and I showed one example, but of course, when we talk about Egypt, there is more details needed to localize this approach for Egyptian weather and Egyptian culture, and also many things. It's a localization, it will be from a lot of perspectives anyway.
Sure. And we
So
have
the
a
answer is
problem
yes.
with the set point, the temperature set point. We don't have references locally to the set point like European.
Ah, okay.
The base, yeah, yes, the base temperature here in our case.
Oh, in our case, okay. So,
Yes.
but actually, is in case we don't have a standard set point, we have ASHRAE. Actually, ASHRAE is American Society Heat Refrigeration Air Conditioning Engineer. So they define for each climate zone what is the set points needed in terms of temperature, humidity in all. So if we don't have it locally from our government,
Yes.
we have it based on the climate zone. We see in which climate zone we are, and then we go to ASHRAE, and then there is definition of all these set points and all thresholds for each climate zone. So we can use it until we have our own
yes.
guideline. Yes.
Okay. Thank you so much. Do we have any other questions? Okay. We have a question from Dwight. Resilience is cost dependent. How we encourage people in local scale to invest in resilience adaptation?
Yeah, it's actually in order to do that, there should be like cost optimality studies to show, for example, what we call it cost opportunity, like what if you didn't prepare and you didn't invest to be resilient? What will be the consequences? And if some events happen, how much you're going to lose? So this kind of cost optimality studies can answer this question. And actually, in order to make like new standards, it need to be cost effective. So like Europe, when it started in 2010, it's ABPD 2010, it started to have a framework. It's called cost optimality framework to upgrade energy code or standards in different countries to be energy efficient, so to be cost effective. Because if it's not cost effective, considering all technologies in the market, you will provide a solution and threshold which is far away from to be realistic. So it's the same for energy resilience. We need such kind of cost optimality framework to be implemented, considering what kind of technologies, what's the prices, what's the uncertainty in prices. And then when we say this is a like threshold and this is a benchmark, it depends on what is the cost-effective solution to make our building is resilient. And in cost optimality, we consider what's called cost opportunity. It means what if the building is not resilient? There will be a very high risk in some situations. So all these things can be considered in cost optimality frameworks for energy efficiency or for energy resilience. And this is actually, now we work on this here also in Europe. Yes.
Thank you so much, Professor Hamdy, for this informative answer. Do we have any other questions? From Dwight also, can you provide us such guide can be used as a starting point?
Okay, so it's like this PhD, which is I presented today. I believe it's a very nice starting point, because as I mentioned, this work started in 2018 and 2022, let's say. So it's a lot of work has been done, and even it's focusing on all the climates, but there is a review about different ones, and also present how to make this assessment in very transparent way. So maybe this is the work come from our laboratory, so maybe I recommend it heavily because I know all the details behind it and also what we found before we developed this work. So I can recommend this one. Okay. And at NTNU also, we are happy usually when someone working on approaches we provide to make collaboration, to extend this knowledge. So one of goals of should be all universities is to spread knowledge. So we will be happy to spread this framework and apply it in different climates. And this is also one of the goals for us to be on this IEA Annex 80, 82, and 96 now, and 93. This is all, yeah.
Okay, thank you, Professor Hamdy. Thank you, Dua, for your question. I have provided the Google Scholar link for Professor Mohamed Hamdy in the chat. You may follow his research through Google Scholar. Do we have any other questions? Okay, as we come to the end of today's webinar, I would like to sincerely thank Professor Mohamed Hamdy for the depth and the clarity he brought to this important topic. His presentation was easy to follow, yet rich with technical knowledge, and it gave us fresh insights into how building energy performance can adapt to future challenges. Many thanks to everyone who joins us this evening. We are always glad to connect with those passionate about sustainable architecture and resilient urban design. Special thanks to Professor 𝗕𝗂𝗶𝗶𝗆𝗆, the founder of Spatial Analysis and Simulation Lab, for always supporting this knowledge sharing community. I'd also like to acknowledge our research team, Engineering Ahmed Fouad and Engineering Mariam Magid, for their outstanding support and efforts. We look forward to welcoming you to our next spatial analysis and simulation sessions. Thank you again and have a great evening. Thank you so much. Thank you, Professor Hamdy. And
Thank you so much.
Thank you so much.
Thank you.
Thank you, everyone. Thank you.
Bye-bye.
See you.
Thank you. Have a great evening. Thank you. Bye-bye.